Okay, let's get started. Let's remember where we were at. We were studying this rat problem. And the reason we're studying this problem is to untangle a couple concepts and exemplify the utility of Gibbs samplers. And this is the historical example as well. So where Gelfand and Smith first started with an application that inspired Gibbs sampling. And I'm not sure what came first. My experience from reading history is Adrian Smith already knows all the answers before he gets started. So, and whoever works with them gets something awesome out of it. And that was Gelfand, a career changer. So, this is the model that they first started studying. This doesn't appear in their JASA paper, but it's the 3 papers that lead up, and one of those I posted to the webpage. And so I do want you to kind of skim through it and see this model and map my notation to their notation, and just bear in mind when I use gamma distributions, they use inverse chi-squareds in their paper, or inverse gammas, something like that. So you'll have to kind of re-encode that and think about it. But what I really want you to do on the next homework, not this homework, but the one coming up where you implement this, is I don't care if you get exactly their parameterization in their model. I want you to pick a couple different hyperparameters in your priors and rerun it and see how stable the answers are. So that's one of my big criticisms in the paper, is they don't really do that. They make choices, and you're kind of hoping those choices don't make a lot of difference, and they do. So, and I'm not saying that they're unjustified choices either. They rationalize those choices in the paper. But anything the answer is sensitive to, I want to tell people. We kind of know that the answer should be really sensitive to data in some ways. In which ways is a big question. So that's inference, like figuring out what it is about the data that tells us about the answers. But also I consider the model part of the prior part of the model. So some people will just say this is the model right here. But I'll say the prior incorporation on everything is part of the model as well. So we're going to study the Wishart distribution. It's going to be the conjugate prior for the inverse matrix, this matrix right here. You could either cut this on sigma scale or sigma inverse scale. So this is just the precision matrix. If you don't like encoding it that way, you can just call it sigma right here and call that the covariance matrix. Which one do you like better? Have any opinions?
Precision's nicer order right now. Probably not enough of the matrix style.
Josiah says he likes precision because it's nicer. But because he doesn't know enough, so he's going to choose one. And I think that's what we usually do.
I saw a lot of stuff online, like putting that in terms of precision. So I guess relating it to the stuff online, I'd probably go with precision because that's what everyone uses, it seems like. So.
Okay, so 2 for precision. Way to go, precision. You know, they're 1-to-1 with each other if you can invert the matrix. So there's conditions on matrices if you can invert them. So if it's positive definite, that'll do it for us. Covariances are supposed to be positive definite, otherwise it's not a covariance matrix. We kind of understand the terms in the covariance matrix. It tells us how things covary together. So there is an interpretation to that, which is kind of cool. I understand covariances. I learned about that almost, first, like in my first stat class that came up. And so how do 2 things vary together? And I can kind of understand that. The precision matrix has some really cool interpretations, and I did give you a handout that I typed up and I put it on the website. So I don't know if you guys have seen that link. It's called the precision matrix. So you can go to the class webpage where I disseminate all the materials. They haven't changed. And there is a link on the precision matrix, and I just typed up a 2-pager for you. So, and it tells you properties of the precision matrix. Has anybody been ambitious enough to just at least glance at that? Christina? Awesome, thank you. What does it say? What's the key point about precisions? It summarizes it at the end. So if you want to ever know what I'm saying, read the first, read the end real quick. Did you pull that up, Zach?
I didn't see that.
No, you didn't see it?
No.
Did you pull it? I just saw you guys go to the computer.
Like right now.
Yeah. The zeros in the precision matrix, it tells you about at the end and how to interpret them. The zeros in the precision matrix tell you about conditional independencies. So it says, given everything in the model, if there's a zero entry in the ij entry, it's saying the ith element is conditionally independent of the jth element. And it's conditionally independent given everything else in the model. So that typical regression, was that me on YouTube or something? So hopefully that was about the precision matrix. So I'll drive for this hour. So the zeros, the ij element is 0 if I is conditionally independent of j. So that means they factorize given everything else in the model. So if you have p covariance, it means the p covariance minus I and j, all the rest of them.
Would that be the same for the covariance matrix?
Yeah. So one cool thing, so I'll give you an example. Think about an autoregressive model. So an autoregressive model has a dependency, so I'll just write it out like this. xt is equal to something, I'll say 0.5 xt minus 1. This number has to be bounded by 1, the norm of it does, for this to be a stationary model. And then this is normal pair. So that's a regression model, autoregressive. There's conditional independencies in here. So just think about t is definitely dependent on t minus 1. Is t plus 1 also dependent on t minus 1? It is. But if I gave you xt, it's not. So that it factorizes. So this is a model for p of xt given xt minus 1. And so if I put in xt minus 2 in here, and all the rest of them, this is really just p of xt given xt minus 1. This has the Markov property, that all the other conditionings fall out. But they are covarying together. So xt minus 2 has information about xt minus 1. All I need to know to generate xt minus 1 is xt minus 2. xt minus 1 has something to do with xt, so xt by transitivity has something to do with xt minus 2. So the covariance matrix for this is dense. All of them have something to do with each other, and as you go farther and farther down the columns, those numbers get smaller and smaller. So there's a decaying relationship through time, but they are related to each other. So the covariance matrix for this is dense. Covariance of, I'll say, x1, x2, x3, so on and so forth, however high you want to go, is dense. And it has this pattern where you have the variances in the diagonal are sigma squared. And the off diagonals start decaying as you start moving farther and farther out. So the precision matrix, so I'll call this sigma. It's not the same sigma here. It's a different sigma. So I'll call it for RAR. So sigma inverse for AR process is not dense. It actually looks like this. It has a diagonal. This thing is full rank. And it's tri-banded. And everything else is 0. So it's telling about the conditional independencies. This has something to do with its neighbor, but given that, everything else in the model, so this given that, has no dependency on everything else. So that's what it's saying. An AR2 model would have 5 bands on it. So the zeros are telling you conditional independencies, that if I'm given everything, so x1 given x2, they depend on each other. They're not independent, they're totally dependent. But this one, x1 given how does it depend on X3? Well, because I'm given everything else, including X2, then it doesn't matter what it is. And that happens in both directions.
So one thing I'm a little bit confused about is in the covariance matrix, your off-diagonal entries are the covariances between I element and J element that is normal. In the precision matrix, the off-diagonal entries, like I would think they would be the precision of the co-precision or whatever that would mean.
Whatever that means.
Whatever.
So you don't even know what it means and you're arguing for it. So what does it mean? And I'm telling you what it means.
I'm just saying that that's what I would imagine that you have an off-diagonal.
You would imagine something that you don't know what it means. It sounds like confusion, and I can clear up this confusion for you by telling you to go read that 2-pager.
Okay.
How about that? So, and I give you the forms, and I give you the updating forms for the inverse and everything, how you would actually computationally update everything, the regression forms of everything, and I give you an explanation. Has anybody ever heard of partial correlations? Where'd you learn about it? Regression class, like undergrad puppy regression, like your first regression class. So it has no technical things, just summation formulas, no proofs, hardly, just lots of statements. When I was an undergrad, I learned about partial correlations. Anybody else want to throw their hat in the ring and say they took an undergrad regression class? Because I know it's in there. Yeah. So the precision elements are the partial correlations. So if you want to go back and review what a partial correlation is, they're equivalent to the precision elements. So there might bridge that gap that it has something to do with something. We don't know what it is. But the zeros tell us about conditional independencies, and they also are the partial correlations. So read through that, and I will omit a whole lecture on precision matrices. So they're things that are useful. So what people will do with them is they'll take data, model it as a Gaussian maybe, invert that matrix in Spirit. You wouldn't actually do it. You do your updates on the precision matrix. And zeros that appear, maybe maximum likelihood estimates of 0 or something like that, are telling us things are unrelated to other things. So if you're studying the stock market, you want to know which stocks covary with each other, which ones move with each other. So if you're building a hedge fund, this is hedge fund 101. So what are the conditional independencies? People call that graphical Gaussian modeling. It's really just modeling the normal. So there's the Gaussian part. The graphical part is by studying the precision matrix and understanding where the zeros are. Now, of course, if you do an estimation, you're never going to get a hard 0. And so you need to impose penalties on things so that you can see what's a hard 0. And when I tell you about Bayesian hypothesis testing, that's ultimately what they do in a big MCMC framework, is they try to, through a point mass mixture setup, try to figure out what zeros are. I'm not going to give you a lecture in that context, but you can apply everything I teach you in terms of regression, where we're going to apply the concept to covariance, and not elements of the precision, but you could apply that same concept to precisions. And so the whole thing is to figure out what covaries together, form them into a group, and show the little edges between everything, where the edges are representing the conditional dependencies. That's a graph. So there's no graph except in your mind, how you think about it. So it's like, but anyway, the graph is related to the zeros of the precision matrix. And so it's a hard problem. If you throw a whole bunch of stuff in there, there's going to be submatrices that are conditionally independent of other submatrices. And the name of the game is to sort that out and figure out which matrices are dependent on other matrices. So if you're building a hedge fund, you might want to be careful and not put all of your money in stocks that always move in the same direction. That works really great if the stocks are climbing in price, but they could all crash in price too. So the hedge means that you need to pick up on things that move in other directions. So you can work against the market sometimes and still be protected when your stocks collapse. So, and different stock markets have different strategies for doing that. So they studied different types of stocks. So one thing that happened when I was a kid, the NASDAQ popped up. So, and the NASDAQ is entirely different than the S&P because the S&P looks at how much actual capital you have and substance you have, where NASDAQ has a whole bunch of tech stocks. So in the 90s, when IBM sold off all their equipment and became a software company, essentially, that didn't quite totally happen, but they used to be a hardware company, and they went to software, they don't have any capital anymore. It's more like what they can do with this thing that they don't have to warehouse. And so the way that they evaluated markets had to change. So out comes another type of stock market. Anyway, I don't know too much about finance, but I do know that. So my friends that work at the Citadel or Goldman Sachs essentially study this and study the inverse covariance matrix. Things like that. Of course, there's a lot of secret sauce in their recipes, how they do that. Okay, I'll let you read the document and you can fill in the gaps on that. But it's essentially stuff that presumably you already learned in a different name. So let's get rid of that. So let me just remind you what we need to do in all of this is we're going to have to estimate this stuff right here. We're going to have to estimate that. So I want to keep in mind we have a model for the alpha i's, beta i's. Typically you would estimate those and put a prior on them. But instead of a prior, I already am treating this randomly. And this creates a lot of confusion just in terms of language. This is what I find people fight most about, is just understanding terms. So I want to just tell you, this is not a prior. Because a frequentist might use this too, a so-called frequentist. I always ask them what type, what guarantees do they give me, that sort of thing. But non-Bayesians use this as well. And it looks and feels just like a prior. This is called a random effect. And I will tell you that non-Bayesians will do this and it looks and feels very Bayesian. So you can imagine a room full of non-Bayesians and Bayesians getting together, writing down a random effect model, and a Bayesian getting confused and going, well, that's a prior. Argument. I've heard this for like 45 minutes where it's like, you would just let it go. If you want to think of it as a prior, I guess you could. But again, I think of the prior as your model. Everything you're doing. The reason you're establishing this prior right here is to account for all the rats have their own effect and they're more tied to each other than other rats. And so the alpha I, beta I are the rat parameters. And so I want to associate each rat's time period with that rat. And so I want variability between the rats and variability within the rats, and I want the variability between the rats to be bigger than the variability than within the rats. So this gives me another mechanism to model variability. So this is the rat's variability for its model parameters, and this is the variability of its weights in a time series. And so this is a standard statistical modeling technique that if you think that groups are more related with each other, you might consider a random effect on that group level. Let me give you just another example, just to fill in the gaps. This might be in Wikipedia or something like that. There's lots of examples out there. But imagine our instructors at Virginia Tech. So they teach, let's say, calculus. Do they still do that? Do they still teach calculus? I think they do, you know? I worry about this math info thing. So anyway, if it's a robot teaching them or if it's actually a human teaching them. Anyway, I think that they have instructors, collegiate faculty members, professors of the practice, and they'll go around and they'll teach these large classes. So, and they might get 5 of them. So per semester, something like that. Typical thing, they're teaching 5 sections of calculus. And there's another instructor that teaches 5 sections of calculus. And there's reason to believe that instructor 1's classes look like a certain distribution, and instructor 2's classes look like a different distribution. So you can imagine there's a teacher effect on the class. And there certainly is in my class. Like, my distributions don't look like some other faculty members. So what do my grades mean? They might mean different things than other faculty members. So my A's don't mean very much, but my C's certainly do. You know, where some people, it's like their average is a C. And so that doesn't mean they're bad. So an A means something amazing to them. So, and it's a little bit different for me. So you can imagine that the teachers even try to standardize their strategies for teaching. I've seen that. But it's not perfect. So some people just present in a different fashion that illuminates people a little bit more. So there might be a teacher effect, there might be a classroom effect. So you can put random effects within random effects. So and have parameters relating just to the classroom. And so you can try to isolate those. So this isn't a prior, but it looks and feels just like a prior. So if nobody told you that it was not a prior and just said, go calculate, you would act just like a Bayesian. And a non-Bayesian would do the exact same thing, and they would build what I would call the posterior distribution. But if I called it that to a non-Bayesian, they would freak out. And so I don't want to fall in that pitfall, so I go, oh, it's a random effect distribution. So the not posterior distribution that we could compute by banging this into that, multiplying the model for the weights into this, I could come up with something that looked like Bayes' theorem. It is Bayes' theorem. And I would just call it something different. And the reason we distinguish it is because it's a mechanism of modeling. So we're modeling this and we're trying to understand if the initial rat's weights have something to do with the propensity to put on weight through time. Okay. Now a Bayesian might come in and they might say, I also need a prior on phi. So we need these. And we need a prior on sigma. I'm going to choose to put it on sigma inverse because that's the Wishart conjugate. On the homework, I asked you to work in the other direction. That I have you working with sigma, and you will need to go to an inverse Wishart table to look up that formula and see how it's parameterized. So that will be the name of the game. So when you're plugging off the mean, you're going to be pattern matching. And so when I'm looking at all of this, I can recognize some terms and it tells me what other terms are, just like a gamma. And if this didn't say trace and you interpreted everything as scalars, you would think this was gamma distribution. It looks just like it. So this is the higher dimensional thing. I haven't told you what K is, but it's the dimension of the matrix, and I'll tell you about this formula later.
I was actually going to ask that before. If sigma was a 1 by 1, then would this just be a gamma?
Yes.
Okay.
So keep in mind that's inverted, so it'd be the inverse thing. So they relate back to each other in the opposite.
So what Wishart is an inverse gamma with a 1 by 1.
Yes.
Thing.
So if you ever get confused, just remind yourself it's the other one than the one that I'm thinking. And then go grab a book and make sure you have it right. The reason I wrote this formula down on the board is I don't remember all of it all the time. I always look it up when I'm playing around with it. If I'm doing a lot of model selection, I probably know what it is off the top of my head. So apparently I haven't done that for a couple of years, so I had to look up what all these parameters were. Okay, back to the rat model. So we might pick this, and we might pick this to be Wishart. We'll show that this is conjugate. Probably pick this to be gamma. That's also conjugate. And so I don't need a prior in the alpha i's and beta i's because I've got the random effect distribution that looks and feels just like a prior. So random effect distribution, if you call it a prior and you walk into a non-Bayesian meeting, prepare to waste hours on terminology. And prepare to waste hours tonight, all by yourself, on terminology. So I've said what I have to say about that. So, and we also need a prior on these. Beta naught, and I'm going to just nickname these things. I'm going to call that theta naught, and I'm going to call that theta I. So it'd be a little bit easier to work through this in matrix notation, and that's what I'd recommend you do in your homework, and work in inner products and outer products, and do not work in sums of squares notation. So otherwise, you'll never code that thing up properly. You want to work in matrix notation. It's faster. It's also easier to recognize once you get the handle of it. So we need this right here. Theta naught, and this would be a normal, and that's the conjugate choice right there. So let me just write down what the likelihood looks like. How do I write down a likelihood function? I write down the sampling function first. That's all I do. So I'm going to say this thing is PWIJ given alpha I, beta I, and phi. That's my notation right here. So this is the notation I like using. It makes me feel good because I can remember what all the parameters are. So I can rewrite that right there as theta I. This also has t in there, so I'm gonna, usually I put an x in here to denote that there's conditional on data, but it's just conditioning on the time point, the way you've scaled the problem. So make sure if you're gonna use this model, the time points are scaled in a reasonable way. So that's what this model is right here. I want to just point out, this thing is theta I transpose times 1t. So theta I transpose is going that way, and I'm dotting it into 1t. And that is equal to beta I, alpha I, beta I times t. So I would use this notation when you encode your normal. It'll make everything a lot simpler. So let's just write down what this looks like. So when you're trying to rearrange everything and figure out what the full conditionals are, this is the part you need to stare at. Until you have the likelihood written down, don't even bother. So trying to recognize the full conditionals. This is how I do it. I write down the sampling model. So I'm going to say for rat I, I've got a model that looks like this. This is t goes from 1 to cap t. So some of you are going to ask me what the ends of the bounds are. On the likelihood, pick some. You know, you can pick up the numbers to be in the paper. For this exercise, you're just writing something down on paper. So just pick your own indices. So to cap t. And this is going to be PWIT given theta I and phi. So that's the model for the weights, conditional on everything else. But I had to select the rat parameters, these things right here. I had to pick these beforehand. So how did I do it? I sampled from the random effect distribution once for rat I. I don't sample t times for rat I. They have their parameters. They were drawn once. So this is going to be whatever this distribution is. Let's just call it pi theta I given theta naught and sigma inverse. So that's what that looks like right there. So that just has all these parameters. That's theta I, that's the theta naught, here's the sigma inverse, and I just bury that in terms of notation. So I draw that once for rat I. This is going to be pi theta I given theta naught and sigma inverse. So this is multiplied by n once. I sampled that for rat I, and then I generated its time series given those parameters. So that's for rat I. To write down the full model, I think that the key is to make sure these braces are in the right place and make sure you're not multiplying that up a whole bunch of times. To get this thing right, that's the common error. Now I need to do this over all the rats. Pi I goes from 1 to n. That's my rat number right there. So just one more product. So that's what I would consider the sampling distribution. So I could call this f of w, vector if you will. I usually don't use that notation, but just to bold it out. So all of the weights given all of the parameters. is the way I like to think about it. That's the sampling function. And so what are those parameters? That's kind of everything. That's the theta i's, the phi, the theta naught, and the sigma inverse. So if I want to spin this around, I plug data in to it, the w's, and then I think of this as a function over its parameters. So then I rethink about this, and I write this down as the likelihood. So the likelihood of sigma inverse, I'm going to write that down in there because that's all kind of part of it. You struggle with naming this thing right here where it's like, okay, I'm just going to treat it as a function of that, and that's going to be my notation, theta I. It's a function of theta I. That's the model for it. So this is kind of already like in posterior form for this. So that's where everybody will argue, is just over the little nuanced language, because if you are a non-Bayesian, you wouldn't write down these priors, you would maximize over those, but then you would come up with a random distribution for the random effect. What does a Bayesian do? Comes up with a joint random distribution for everything. And if you wanted to maximize over that, you could do that too. So and it might coincide if you use like Jeffrey's priors with the MLE estimates of everything else. So depending on what you want to do, if you want to match your frequentist friends but explain variability differently, you can kind of operate under both lenses. It won't piss anybody off any less. Non-Bayesians and Bayesians, and the word random effect comes up, and oh my goodness. It never seems to get any better. I'm going to write that down, even though this is already kind of in posterior form right here. So this is just a function of all of those things. Theta naught and phi, given all of your data. So what I would do, if I were trying to come up with the posterior distribution on phi, I'd take this prior, I'd multiply it into this thing, and then I would recognize everything in terms of phi. What I can do is I can already remove that thing. There's no phis in here. So what I would do notationally is I just get rid of that. How many times does phi get touched right here? Does it get touched t by n times? It does. So the likelihood would really be proportional to this thing times my prior. So just chuck that away and then recognize everything in terms of phi. Let's do it for theta naught. For theta naught, I would do the exact same thing. I would multiply this function by the prior for theta naught. And I'd notice there's no theta naughts in here, right here. So I would get rid of this whole part, including the product, because there's no theta naughts. How many times does theta naught appear in the likelihood? It's n times. So the key is to have your braces written down correctly. Where does theta naught appear? It's on the outside of this product, but it's being touched by this product n times. So I would write that down for the likelihood and multiply it by that prior. And then recognize the terms, quadratic term minus 2 linear term. Just like on the midterm. No difference. Make sure you do it right, and it's going to look like the solution of a generalized least squares type problem. So let's do it for our last parameter, theta i's. I don't have a prior for it. It's already in here. So I just grab this formula for the theta i's. Where does the theta I appear? It appears everywhere, so I can't reduce that anywhere. I've got theta I right here and theta I right here. So there are some conditional independencies where some of these things fall out as normalizing constants. For theta naught, that whole term falls out. So it only depends on the data through theta I, but theta I does depend on the data. So there's a transitive relationship between all the parameters. So there's a lending of information. And so this is how a Bayesian likes to write down models. They think about all these dependencies and they write down some model. At the end of the day, what Gelfand and Smith did is they wrote down the full conditionals for everything properly and then implemented a Gibbsian. So it's putting together all that stuff you learned about in the last couple weeks and just following some notation. But the key to writing down full conditionals and all of that is writing down the likelihood. Writing down the likelihood is akin to writing down the sampling distribution. The only thing that's different about this is you've got that theta I in there. This already is like the not posterior of theta I. It's the random effect distribution. And if you're following Bayes' theorem, it's already a random variable. So it just has a nuanced different name because it's a modeling tool. And Bayesians and non-Bayesians like that modeling tool. For me, I think I could call that a prior, and I'm using a subjective analysis, and I'm thinking that it's like this, and I'm tying those two parameters together, and it's part of my prior. And that would be fine, but that's not the way Gelfand and Smith said it, and I appreciate the nuanced difference. That my non-Bayesian friends also use something that looks just like Bayes. And as long as I don't accuse them of doing Bayes, all seems to be okay. So I'm happy to play by their language rules, even though I know they're part Bayesians and part non-Bayesians. There's nothing wrong with that either. At least they got it part right. It's a joke. So let's just do it for phi real quick. If we had phi, this would be the only part that we would need for phi, but this gets producted up again n times. So don't forget that product because this is getting hit that many times. Just think about how you sample the data. How would I sample the data? I would sample these first. That happens once for each rat, and then I would sample its t time points. So then I do it again for another rat, boom, then I sample its t time points. This is illustrating that. So the random process for generating the data, think your way through it and think about it in terms of for loop, how you would generate it. All those terms need to appear as functions in your likelihood. Then a Bayesian multiplies by their prior and simplifies everything. And if you just write it out notationally like that, you can do your simplification up front. So let's just remember what maybe this distribution looks like. So I'll write it down over here. This distribution right here looks like this. This is going to be sigma inverse absolute value determinant. I mean to say that. I always just say absolute value sometimes. Determinant and absolute value simultaneously. This is positive right here. E to the minus 1/2 times theta I minus, I subtract off the mean of this thing, theta naught, transpose sigma inverse theta I minus theta naught. So that's what that model looks like. So instead of writing down that pi term over there on the end, I'm encoding it with that thing. I did throw away all my normalizing constant because I don't need them when I'm writing down the likelihood. So that's this part of the model. And I dinged you off a half point if you didn't know what the normalizing constant is. You raise it to the dimension divided by 2, and the dimension of this problem is 2. So it's not n, and it's not some other, it's not k because I wrote that down on the board too. So it's 2. You know, saying that if you did mess it up and you implemented it and wrote it down, wouldn't affect you at all. So it's one of those errors that you get no penalty for, and that's what my minus 1/2 is supposed to imply as well. No real penalty, just let's try to remember it. So question is what does this look like? So what we would do if we were trying to figure out what the likelihood is for this, I would look at how many times this appears. There's no sigma in here. This thing just kind of falls off. So what I would do for this is I would product this up. I goes from 1 to n right here, and that would be my likelihood term. So the likelihood for sigma inverse, given everything else, that's my notation because I get sick of writing all the other parameters down, is proportional to this. It gets producted up that one time. So which prior is conjugate? And so you should stare at this and think about this thing in terms of this parameter right here. And you should be thinking about something that's been staring at you in the face the entire time that I've purposefully squared so I don't erase it, because I can't repeat it. it almost looks like this. There's this little thing in here, trace. So I want to just point out, I can trace this up real quickly as well because this is one-dimensional. So somebody give me the definition of a trace of a matrix. Some of the diagonals. Somebody give me another definition. Some of the eigenvalues. So I would rather sum the diagonal, you know. So, but they are equivalent to each other, and that's kind of cool. That's the trace of a matrix. This is a 1 by 1. So this right here and that, if you multiply them together, it's this thing. If you multiplied this into this, it would be a 1 by 1. If you throw the matrix up in the middle, it's not going to change any of that because it's all conformable. So that's a 1 by 1. So the trace sum of the diagonal element is just that element. So summing it up is that element. So dropping the trace in, no harm. Let me just tell you something about traces. And get rid of the model real quick. Trace of A, B, C. I'm going to assume that A, B, and C are conformable matrices, so I can multiply these together. They don't all have to be squares. So this could be a different dimensional thing right in here, but P times K, K times K prime times P. So it's a square. Ultimately, everything is conformable. They don't have to be the same sizes. So this is true. This is the trace of BCA. This is equal to the trace of CAB. And I can put this one back again, and I'll come back around to this thing. So what I did is I took the A and I brought it over here to get here. Then I took the B over here and I put it here. So traces are equivalent under cyclic permutations. So if you run these things around in a circle, it's the same trace. You can't shuffle them in any old order. And that should be clear by the dimensions I wrote down as well. But if you end up cycling through these, you'll notice that it has to be square, so that thing, when I come over here, it's conformable. Everything is conformable when I run it in a loop. So this is a fact, and I think I asked you to prove this on a homework. So go grab your linear algebra book, go look at Wikipedia, Stack Exchange, or just show. So, yeah, and actually do the proof yourself. So, and you'll start exciting that part of your brain to do the proof yourself. But if you want to go grab your elementary textbook, it's in there. So that's a fact. So I can spin this thing around. This is sigma inverse absolute value e to the minus 1/2 trace. And I can spin this thing around right here, bring that one over here, and then bring that over here again. So 2 steps of this. And what I'll get is theta I minus theta naught, theta I minus theta naught transpose. Boom, boom. Sigma inverse. Now this looks like that. So now they look exactly the same. If I caught this up the n times, so I didn't use my n right there, I just it would start changing the exponent on all this. I want to point out, you probably recognize this like this, that we always divide by the inverse matrix and take the determinant. Determinants have a nice property that I can always take the exponent and drag it inside. That's really nice to be able to do. And just drag that back and forth. That always works. You can prove that too if you'd like. So, determinants are homomorphisms. I took an abstract algebra class once upon a time, and this was something we had to go home and write like a 4-page proof on. Where it's like, just do an example and show that it's the same. Yes, please.
Isn't it less computational intensive to just put the inverse outside the cavity?
Doesn't matter if you already have the covariant or the precision matrix and you're operating on that scale, then probably, so if I'm only updating in an MCMC fashion and I'm working with the precision matrix, I'd probably not do inverse in every time. I would just call it something different.
Yeah.
So yeah, I never actually invert in the middle of my codes. If you do, lots of errors lead right through that pipe. So this thing looks like it's inverse Wishart. That's the parameter. Here's the parameter right here, and here's the parameter here. So I want to just point out that V in this notation is a K by K, positive definite. Lambda is a scalar. And omega is also a K by K positive definite. I want to just point out these are the expectations and the variances, and a lot of times when I interpret parameters, I think about it through this lens real quickly, see if it relates to anything outside it. So this matrix right here has something to do where this thing is centered. Not quite. It's being scaled also by this thing right here. Very often what I will do when I'm writing this thing down, I'll often work with this. I'll write it this way. So whatever that is and whatever that is, the expectation of this thing, given all the stuff, is equal to omega over gamma times gamma, which makes it omega. So if I write out the model like that and I use this, when I encode things, I can think about where I'm centering these matrices. So this is a distribution over matrices. The matrices, when parameterized in this fashion, are everywhere I see an omega, I just divide it by that same scalar. Everything is centered in this matrix right here. And gamma is acting like a diffusion parameter. And it's controlling the variability of everything. Vij and Vii are the elements of the V matrix. So that's what it is. So gamma, if it gets bigger, you're making the distribution wider, meaning that we get farther and farther away from our centering matrix. If I were doing an analysis and I was trying to figure out if there are conditional independencies in the model, what might I pick omega to be? I probably wouldn't pick it to be dense or anything like that. I would probably pick this thing to be the identity. Because if there are zeros that appear in everything, or non-zeros that appear, and it's saying there's dependencies, I want the data to tell me that. I don't want to impose that dependence maybe through my centering parameter. So depending on what you're doing with this analysis, might guide you into how you pick these parameters. They did it in a RAT paper, and they had some choices for this as well. So you'll have to map over to their notation and see what their choices were, and you can read the paragraph and see if it was convincing. My recollection, I didn't read the paper this year, was that I'm never convinced when I read through it, and I just have this subtle feeling that they just did this to highlight Gibbs sampling. And they worked with the scientists, they knew what the answers were that they wanted, and they just wiggled these parameters around. It kind of feels that way because where they come up with these numbers, and when you read the paper, you might feel similarly. So I think they're data light for this analysis, and they kind of know certain things they expect to see for it to make sense, and they probably did some prior hacking. So on everything, and maybe that made sense to them and they didn't want to encode all that into the model. or set these constraints or something like that. I'm not sure. I never asked them because I read the Jazza paper first, and then I came across this and saw what they were doing. I think they were just trying to satisfy a scientist, coming up with some relationships, knowing some relationships, turning some knobs so that it did what they thought, and then they inferred the rest out of it. And I think a lot of people do things like that. It's like the ultimate subjective analysis. So, not super compelling, but still groundbreaking in the sense that they're the first one to try to infer all these parameters jointly. And that's kind of cool. So I understand the dependence between matrices and vectors and scalars. There's phi over there as well. So it's this joint distribution of all of these things. And so the Bayesian is at liberty to put random distribution on anything and make joint distributions out of that. And then if they want to understand that distribution, they go to Gibbs sampling and they run the tool, and then they finally converges to some posterior distribution. And so they assess their convergence, and that's what you'll do in the next homework. And you'll have well through Thanksgiving break to do that. I know the calendar doesn't say that. You're welcome, Zach. So yeah, we will extend on that. That's the only thing that makes sense. And you'll be able to implement that really quick. Plenty of time. I think what I'd like to do is come back next time and show you more explicitly that this is the conjugate analysis. I want to move away from the rat example just for a moment because I want you to do that one for your homework. Probably do that tonight or tomorrow night. And I'll do on Friday the more arbitrary example where you're just working with joint normal data, and then we'll just look at the expectation of that analysis. We'll talk about what it all means and see that it makes sense and it coincides with our non-Bayesian friends. I'll point out this thing right here is an outer product. This is a matrix, so, and it's conformable with that, and so it's taking the place of this thing right here. And so we'll be able to understand what the expectation and the variances are by looking at these formulas. And I just want to walk you through 15 minutes of that and show you that these distributions make sense as well. And they have little nods, the hyperparameters that you can kind of control and see what they mean. And there might be some obvious choices that you pick. For the problem in the homework that I gave you, and I gave you a prior that's proportional to something, that is the Jeffreys prior. So you might think, where did I come up with it? It's a limit of this distribution, no surprise, and it's the Jeffreys prior. So I didn't derive it, I just read it from a book and wrote it down for you. I'm sure we could all derive it though. So we probably won't do that. I'll also mention I'm not going to have you memorize what a Wishart distribution is. It won't appear on any of the tests, but we're going to feel comfortable with it after working through the homework. Cool. Thanks, you guys. We're going to jump into hypothesis testing next. My absolute favorite topic.